This conference will now be recorded.
Very good evening, students. Today, I have come up with various previous test questions on the topic Gauss's law, which comes in electrostatics. In fact, we have Gauss's law in magnetostatics as well. But here we are going to discuss some questions which are being asked in various competitive exams like AIMS, NEETs, and also the questions which are being asked in the board exam also in some cases. So these questions will actually build your concept a little better, with which you can be able to solve various other problems if you are thorough with this. Okay, so let us start our discussions for today. So the questions on Gauss's law will be discussing today. Okay, so this question says two infinitely long parallel wires having linear charge densities λ1 and λ2 respectively are placed at a distance capital R. The force per unit length on either wire will be. Okay, so the question is basically saying that there are two infinitely long wires. Sorry. Like this. They are kept R distance away from each other. Okay, and suppose this wire has λ1 charge density and this has λ2. Since these are linear charge distribution, so these are having linear charge distribution, so lambda is actually charge per unit length. Charge per unit length. Okay, now the question is, if these two wires are like, if these are situated side by side and both of them have charges, so what will be the force acting on either of these wires? Okay, what will be the force acting on either of the wires? Okay, so we have to calculate that. So similar to the parallel wire carrying current in a magnetic field, right? Or parallel wire, see, if there are parallel wires carrying current I1 and I2 separated by some, we have calculated the force between them. But this question is in the electric field now. So how do you find out the force? And see, the topic we are discussing here is Gauss's law. So obviously we'll be able to take the help of Gauss's law. So how, see, if I have a point charge over here, suppose some charge q over here, okay, and some other charge small q over here, so how do they exert force on each other? That concept you have to be clear with. Okay, so you have to be thorough with this particular concept, that how a charge is exerting force on the other one. Okay, and in fact the force will be the same. Force exerted by small q on capital Q or the force exerted by capital Q on small q will be the same. So how do you understand that? How, like, so this is the main concept here. Actually, you know what happens? See, if I just want to find out what is the force on small q due to this capital Q charge at this particular position R, so what I have to do, I have to find out the electric field produced by capital Q at this particular point where the small q charge is there. So the field, I have to find out what is the electric field at this point. And as you know, that electric field, within that electric field, if you bring another charge, it will exert a force, and that will be E into Q. Okay, this is the force. So this is how we actually calculate the force, or this is how the force actually acts, or one charge interact with the other one. Okay, so here what you have to do, you have to find out electric field. Suppose I want to find out, suppose this is the wire 1 and this is wire 2. Just I want to find out force on 1 due to 2. So what I have to do, I have to find out the field produced near the, or produced at the place of wire 1 by 2. So I have to find out electric field due to lambda 2, and then I have to multiply the charge due to this one. So here I have to find out force per unit length. So I can write down that it will be lambda 1 into electric field produced by lambda 2, or the line charge having charge density lambda 2. So let us find out what is the electric field produced by a long wire, infinitely long wire. So here, you know, we have to apply Gauss's law. So, you know, I have to just take a cylindrical Gaussian surface for this. So what I have to take? Gaussian cylindrical surface. Cylindrical Gaussian, I'm sorry. So cylindrical Gaussian surface I have to consider at a distance capital R. Okay. So it had charge density lambda 2. So I hope you have already learned it. So the electric field, you know, electric flux, you know, flux is actually E dot ds. E dot ds. Okay, E is the electric field. Direction of electric field is always radial. In this case, always radial electric field. Okay, like this. Now, due to this flat surfaces, electric field, like electric flux will be 0. So only the curved surface will be the electric flux. So there will be flux through the curved surface. So you know, Gauss's law we apply. If we apply Gauss's law, we know for a closed surface, E dot ds is equal to charge. Suppose I have considered a Gaussian surface of length L. So lambda 2 into L divided by epsilon naught. This is the Gauss's law. Now what is E? E is anyway will be constant throughout the surface. So let me just keep that out of the integration. And here one more point is that for this curved surface, see, electric field as well as the ds, they have the same direction actually. So if two vectors are having same direction, a dot b, that will be ab cos of 0. So cos 0 degree. Okay, if both of them are in the same direction, then I can write, see, I can get rid of this vector sign. So ds, okay, so lambda 2 into L divided by epsilon naught. And see, this area is the area of the curved surface. So 2 pi r L into E, and this is lambda 2 into L by epsilon naught. Okay, so this L and this L will cancel each other. So what will be E? E will be lambda 2 by 2 pi r epsilon naught. So this is very known result, isn't it? So look, now this can be even written as, See, in terms of K, if I write K is 1 by 4 pi epsilon naught. So this one I have to then write 2K in terms of 2K lambda 2 by R. So this is the electric field, and that is produced by lambda 2 charge at the other at the place of the other wire. Now see, if I put this value, the 2K lambda 2 divided by R into lambda 1. So what I am getting? 2K lambda 1 lambda 2 by R. Okay, so look this, option 2 is the correct answer for this question. Okay, so dear students, I have done it rigorously so that you can memorize or you can just brush up your derivation part. But see, in exam what I would have done, I would have written directly the electric field itself, lambda divided by 2 pi epsilon naught R. So I'll just directly write, or I can write 2K lambda by R. I will write directly this result and multiply the charge per unit length, that is lambda 1 here lambda 2. So I'll directly get within a minute. So this was not a very good, very tough question. It was a good question, but not a tough question to solve. Okay, let us go to the next problem. Okay, so you have to choose the correct statement regarding electric field lines. Okay, electric lines of forces. They emerge from negative charge. This is very, very wrong. See how we know electric line of forces. It starts from positive charge, ends at negative charge. Okay, so first option is saying that they emerge from negative. No, that is not. Okay, the electric field line, sorry, electric field in that region is weak, where the density of the field lines of force are more. No, this is just opposite. If you have field lines like this, at some places density of the field lines is more than any other places like this. So here the density of the electric field line is less. So you know, if the electric field strength is E1 here and E2 here, obviously E1 is greater than E2. So electric field strength will be more when the density of the field lines will be more. Okay, they are in radial direction for a point charge. This is very, very correct. Suppose the point charge is there, so due to a point charge, how will be the electric field lines? They will be going like this, and in fact they will go to infinity, where they will meet with the negative charge like this. This is due to point charge. Okay, so this is radial. This is very correct. They have a physical existence. No, they don't have physical existence. Actually, Michael Faraday, he had just imagined, just to understand the field, okay, just to understand the field, he had imagined field lines. Okay, so they don't have physical existence. All right, so in the definition itself, we know electric field lines are the imaginary lines, isn't it? All right. Okay, now what is this question saying? A solid sphere of radius capital R is charged uniformly. A solid sphere of radius capital R is charged uniformly with a total charge of capital Q. Okay, let me just draw the situation. It is, just imagine this is a sphere. Let me okay, anyway, just take it as a sphere. So uniformly charged with total charge Q. Then the correct expression for the electric field is, so this is a solid sphere. Solid sphere means there is charge everywhere inside and out and on the surface also. Okay, so there is charges over here. So charges are there inside throughout. So it has got a radius capital R. Now see the question saying which of these expressions, okay, which of these expressions will be correct for this particular solid sphere. And obviously this is electric field, the expression for the electric field. Okay, so this one is saying that it will be kq, k is 1 by 4 pi epsilon naught, this is k. So it is saying that in any inside point R, the electric field will be like this. So it is varying or increasing directly proportional to the distance inside when it is inside the sphere. Okay, so when it is outside the sphere, it is kq by r square, and 3 says it is 0 at all points. 4 is saying 1 and 2 options are both true. So the fourth option will be the correct answer for this question. Say if I am going to derive this, it will be really lengthy, but still I'll just say something here. See, electric field for a solid sphere vary like this. Suppose this is up to the surface, this is small r is equal to capital R. Okay, so electric field inside a solid sphere will be varying directly proportional like this. Okay, is directly proportional to R, and outside the sphere it will be varying as 1 by r square like this. Okay, so varying as 1 by r square. So the same thing actually for gravitational field also. Gravitational field intensity, that means, yeah, gravitational field intensity. In case of gravitational field intensity also the same variation you will be able to find. Okay, so this is very general question and also very important. In many cases you will see this question in many competitive exam. So I'll just quickly do a little bit of derivation for this particular case. Let me tell you. See, it has total charge q, and throughout the sphere, since it is solid sphere, it has a charge. I have to apply Gauss's law, E dot ds, since the electric field will be always radially outward. Okay, so the unit vector for the surface spherical for the sphere is same as the direction of the electric field, so we can just get rid of the vector sign over here. So E ds, integration E ds is equal to the charge enclosed by the Gaussian surface. Suppose the Gaussian surface is inside. Okay, this is small r, but this is capital R. This is the radius of the sphere, and this small r, suppose at any p inside any point p which is inside the sphere, I have to calculate the electric field at that particular point. So here you have to take the area. See, electric field is constant throughout the surface of this particular Gaussian surface, and so this is ds, and this side the charge enclosed by that particular spherical Gaussian surface, okay, divided by epsilon naught. So q enclosed by epsilon naught. Now see, this surface is 4 pi epsilon naught small r square, because now this is the area, and on the other side the charge enclosed by that Gaussian surface is different than the total charge, isn't it? So this part is enclosing some charge which is not equal to capital Q. That you have to find out. So for that, you know what you have to do? You have to find out charge enclosed. How? You have to first find out what is the rho, the charge per unit volume into the volume of that particular Gaussian surface. Okay, like this. All right. So what is rho then? Rho is the total charge divided by the total volume of the sphere, capital R cube, and this say 4 pi R cube. So this 4 pi will cancel each other, and see here I am getting Q enclosed. I am getting as Q R cube by capital R cube. Now just put it here. Electric field is equal to Q enclosed is Q R cube by R cube epsilon naught, and here it was 4 pi R square. Okay, let me write it here, 4 pi R square. So see this 4 pi R square, 1 by 4 pi epsilon naught, let me write it here, 1 by 4 pi epsilon naught into, see this is square, this is cube, so I can write Q R divided by R cube. Okay, now this particular term I can write as K, so K Q R by R cube. This is a very simple one. Okay, so for the outside, so see, look, this is for inside point, we have got the same thing. Okay, and for outside point anyway, outside point means the whole charge itself will be enclosed by the surface area. So in that case, you know, it will be 1 by 4 pi epsilon naught R cube, sorry, Q into 4 pi epsilon naught R square, small R square itself. So this is actually the field inside a solid sphere. Okay, let us go to the next problem. This is actually very interesting problem, and based on the properties of field lines, here the question says which one of the following pattern of electrostatic field lines, okay, or electrostatic lines of forces is not possible. Okay, which among these four pattern, okay, which among these four patterns is not possible for electric field lines? See, this is for uniform electric field lines. This is possible. For a point charge, it is radial. This is also possible. See, if I just take this particular portion, see, just cover with this, then you have this one. So electric field lines will be diverging in nature. That is also fine. So 4 also correct. So only thing is this one. So this one is not correct actually. This is not possible. So why, you know, what is happening here? You see, electric field lines are actually closing closing. Okay, so making a closed loop. Electric field lines will never form closed loop. Here this is a closed loop. So electric field lines, okay, electric field lines of force, or electric field lines, let us say electric field lines never form closed loop. Okay, so that means, you know, see, electric field lines actually emanates from or emerges from negative charges and meet at what? I'm sorry, field lines are emanating from positive charges and they are just meeting or ending at the negative place. See, this doesn't go like this. Okay, this doesn't go. See, it goes and ends here. Okay, so if it does, so then what happens? You know, the electric field lines are starting from positive charge, say, and then they are ending at the same point. Okay, ending at the same point if they form closed loop. So this is violating this particular property. So electric field lines will be always emanating from positive charges and ending at the negative charges. So that is actually the property. So this means actually when I say that electric field lines are forming closed loop. That means, you know, we are saying that the electric field lines are starting from positive charges and go through all over and then come and ends at the same point. It is not possible. Okay, that's why closed loop will not be the pattern of electric field lines. Now see here, the question says a sphere of a radius capital R and charge Q placed inside a concentric imaginary sphere of radius 2R, then flux associated with the imaginary sphere is. See, suppose there is a sphere, real sphere. It has radius capital R and it has got charge Q. Now if there is another concentric sphere, that means the previous sphere is placed inside a concentric imaginary sphere of radius 2R, okay, like this, then what will be the flux associated through or associated with this imaginary sphere? See, we know flux is what? Flux is this EDS, and this can be denoted by pi also due to electric field. So pi E. Flux will be always charge enclosed by the reference surface or the Gaussian surface divided by epsilon naught. Here, since this bigger surface or the imaginary sphere has bigger surface and it is enclosing the whole charge capital Q, then what is the total flux? Flux associated with the outer sphere, that will be Q by epsilon naught. This is the flux. Okay, I hope you have understood. So Q by epsilon naught is the flux. Okay, now this question is, I think, related to solid sphere itself, but it is for non-conducting solid sphere. The situation is same actually. For conducting solid sphere, whatever charge you give here, so that charge will come on the surface. But for a non-conducting solid sphere, the charge will be residing throughout the volume of the sphere. Then rest of the things are already discussed. So look, the magnitude of the electric field due to the sphere at a distance r from its center. So here r is varying from center, and you have to say how the electric field vary with this r. As I said, if I draw the same figure again, see, this is small r is equal to capital R, that is the radius of the sphere. So up to the surface, okay, up to surface, it varies as or increases directly to the distance. Okay, it is directly proportional to the distance from the center of the sphere, like this. Okay, so this is, so the first option, this is electric field, sorry, yeah, so electric field increases as r increases. So this is true actually inside the sphere. Now electric field decreases as small r increases between 0 to r. That means, so everywhere 0 to infinity, everywhere the electric field decreases. That is what it is saying, so which is not true. Decreases as r increases for r greater than, smaller greater than r, and between, so infinity. So this is actually so this is greater than the radius, that means outer point. Okay, so this outer point, at any outer point, but it is not going up to infinity obviously. So what is the variation outside variation will be 1 by r square, like this. So E like this, so it is decreasing. Okay, so outside the sphere it will be decreasing. So C also will be this correct answer. And C is discontinuous at r is equal to 1. This is also not true. This is not true. Okay, so A and C will be the correct answer for this question. So A and C is this one, first option. All right. So these are the questions from Gauss's law we are discussing from the particular chapter, electrostatics. So what is this question saying? This is saying, so 20 microcoulomb charge is placed inside a closed surface. Let us take any arbitrary surface, closed surface, somewhere 20, like somewhere inside 20 microcoulomb charge is placed. Then the flux linked, so flux linked with this surface will be phi. It is saying that. Okay. So we know flux will be the charge enclosed by the surface, if it is enclosed surface, and then the flux through that surface will be the charge enclosed, this into -6 microcoulomb divided by epsilon naught. Okay, this is the flux, and that is given as phi. Now if another charge 80 microcoulomb is added to this, okay, or placed inside the surface, then what will change in the flux? Let me write this flux as phi 1, and the next, when the charge is added, what will be the flux? So now here the charge enclosed by epsilon naught, so this will be 100 into 10 to the -6 microcoulomb. So this is coulomb now divided by epsilon naught. So total charge enclosed by the surface divided by epsilon naught. So this is the difference. See, now it is actually becoming 5 into phi 1. So now what is the difference or change? Change in that is phi 2 minus phi 1. So what is phi 2? Phi 1 minus phi 1. So this is 4 phi 1. Okay, this is 4 phi 1. That is the change in the flux. Okay, now let us go to the next problem. All right. So what is this question saying? In a region of space, electric field is given by this. E is equal to 8I plus 4J plus 3K. Like that, electric field is given. The electric flux through the surface area of 100 unit. What will be the flux in unit of XY plane, or in the XY plane? Suppose I have, see this XY plane, that means, you know, like this. This is the XY plane. Suppose this is Z. This is Y, this is X. This is Z. Okay. So you know what? Flux, the electric flux through a surface area, how does it go? See, suppose this electric field vector, see, electric field has three components, Ex, Ey, Ez. Now which one will actually produce, or will, like, due to which one, Ex, Ey or Ez, due to which component of the electric field there will be associated flux? Since this is XY plane, we need to know, see, the electric field and the area vector. Area vector must be perpendicular to each other to get the maximum flux. Okay, to get the maximum flux. So in this case, you look, since X to Y components are lying on the plane itself, so those will not be able to produce any flux. Okay, Ex and Ey, they are lying on the plane itself. So the component of the electric field which is perpendicular to this surface xy, that is actually Ez. So this Ez will be producing flux through this, okay, xy plane. So I hope you got the point. Now see, now it is easy. See, flux is actually area into the electric field. So in this case, flux will be area has been taken 100 unit into the electric field, component of the electric field along z direction, that is 3. So this will be in the given units. So this is 300 units. Okay, 300 units. So option 2 will be the correct answer for this question. Okay, now this question is saying that the electric field is 100 volt per meter at a distance 20 centimeter from the center of a dielectric sphere of radius radius 10 centimeter. Then electric field at 3 centimeter distance from the center of the sphere is. Let me tell you this. This is a non-conducting or the dielectric sphere. That means, you know, they have charges inside or throughout the volume. That means solid sphere case. And see, the electric field is given. The electric field is given as 100 volt per meter. Where? At 20 centimeter. Okay. So suppose this has got radius capital R. So small r at any point. Small r, suppose here. So this is the small r is greater than actually capital R. The given case. In the given case, see the electric field we know for any outside point. So this electric field is for outside point as you see in the figure. Okay, so for any outside point, it is k q by r square. K q by r square. This is the field in the outside point. And this is given as how much? 100 volt per meter. This is actually electric field. Okay. Now see, if my distance here small r is actually 20. So then let us find out what is kq, for which there is no any information. So this is actually 20 into 10 to the power minus 2 whole square into 100. So we will get kq from here. See, I'll get like this and this 2 to 4. So I'll get actually 4. So this is the value of k into q. Now we have to find out electric field 3 centimeter. I'm sorry. So here, okay, yeah. So 3 centimeter. From here, let me write down the expression. We have already written down the expression for any internal point of a solid sphere, how the electric field will be. So electric field at the internal point. So see, this is 3 centimeter, but the radius is 10 centimeter. Okay. So this r is equal to 3 centimeter is less than 10 centimeter. So electric field inside will be varying as KQ R by capital R cube. So here KQ, value of KQ we know, that is 4. What is R? R is 3 into 10 to the power minus 2, and R cube, capital R cube, I'm sorry, yes, so it is okay. So this is 10 into 10 to the power minus 2, like this. Okay, so if I solve it, let me just claim this portion. Anyway, you have got this value. So this is 12 10 to the power 4 will come from down here, and 10 to the power minus 2 divided by 100. I'm sorry, this 100. Okay, divided by 100. Okay, so from here we can get actually the 2 will be from here. Somewhere I have done some mistake. I need to cross check. From here, let me find out KQ. R square, small r is actually here 20 centimeter, 20 into 10 to the minus 2. So from here actually we get just 4 only, fine. Then 4th is okay, so this is also fine. Inside point, this is the distance variation, that is 3. KQ I have got 4. Oh, I see, this is actually Q. Q means one more will be here. Is it? Just a minute. Yeah, there is a subtle mistake here. This is 3. Okay, RQ. So let me just redo this calculation. So this is 10 to the power minus 2. Okay, so here this also will be having minus 6 actually. Okay, so this will give you 10 to the power 3 from here. So it will give you eventually 120 volt per meter. Okay, so option 3 will be the correct answer for this question. Okay. Okay, so let us go to the next problem. Okay, so what is this problem saying? If electric flux entering and leaving a closed surface is phi1 and phi2 respectively, then the electric charge inside the surface, suppose there is a surface, any arbitrary surface, so some flux are entering, so that is phi1, and some fluxes are, see, some flux are going out. Okay, so if these two are not equal, then the remaining, see, there will be some flux which will be actually enclosed by, or which will be remaining here. Okay, so what is that flux? So that is actually phi1 minus phi2. If pi2 is leaving, pi1 is coming, then pi1 and pi1 minus pi2, this much is actually the flux which is enclosed or associated with this surface. Now we know flux is equal to q by epsilon naught. Okay, so I have to find out what is the charge enclosed inside. So that is actually q into epsilon naught into phi. So epsilon naught into phi, so this pi is actually here pi1 minus pi2 into epsilon naught. So this is what I'm getting. So very much possible this. Okay, I don't know why they are writing pi2 minus pi1, because entering and leaving, which one is entering? Okay, so generally there is a convention, so which one is entering is taken as negative, so that's why they have written here like this, and what is leaving is positive. So that's how they have done this. So anyway, the option 2 will be the correct answer for this question. Okay, now this is again a very interesting problem. So what is this problem saying? The total flux associated with the given Q will be where A is the side of the Q. See, there are different charges at different corner. Okay, so there are 8 corners and 8 different charges are given. Now you have to find out what is the flux associated with the total flux associated with this Q. So as we know, when we have a charge at any corner, it will be shared by, so if this is charge Q, then it is shared by some 8 sphere in the space. So it will be shared equally by 8 sphere. So what is the effective charge for this particular Q this has? Okay, so I have to actually find out what is the total charge enclosed by the Q. Then see, the flux will be charge enclosed divided by epsilon naught. So how much is the charge enclosed by this, like effective charge enclosed over here? So look, I can write actually 1 over 8 into whole charge, because each charge will be shared by 8 equal such cube. So each cube will have 1/8 of the individual charges as the share for a single cube. So for this cube, how much is the total charge, effective charge? I can just add this, see, 4 plus 2 plus 1 plus, so 4, 2, 1, and this is 3, plus 8 plus 7 plus 5 plus 6, like this. So I have 4, 4, 2, 6, 7, 10, 18, 25, 25, 30, 36. So I have got 36 by 8 into 10 to the power 6, right? 10 to the power minus 6 coulomb. This much charge enclosed by the cube over here. Now let us put it here. Let us put this here. So how much it is? 36, right? 36 divided by 8 into epsilon naught. Okay, let me then clean this portion. Anyway, I have got the total charge. So flux will be q by epsilon naught. So charge enclosed is given here. Look this. Charge enclosed is 36 by 8 into 10 to the power minus 6. Now see, this value was given 1 by epsilon naught was given as 4 pi into 9 into 10 to the power 9 in SI unit. Okay, let us put this here then. So 36 by 8 1 by epsilon naught, this will be multiplied in the numerator only. So this is 4 pi into 9 into 10 to the power 9. And there is 10 to the power minus 6 as well. So these two will make balance. See, this is 2, this is 18. So 18 9s are 162 and pi will be 5 and this will be 10 to the power 3 and flux, unit of flux will be Newton per coulomb into meter square or Newton meter square per coulomb. So this is the unit of the flux. And see here 162 pi, see this option 2, that is going to be the answer for this question. Okay. Okay, I think with this we'll stop this class, and by that we'll be completing the discussions on the questions, various type of questions on Gauss's law. So what is this question saying? The question says a point charge is placed at a distance a by 2 perpendicular to the plane at a distance perpendicular to the plane above the center of a square of side A. That means, you know, you have, this is very familiar problem to you, I guess. So this is suppose a square. Okay, these sides are A. Okay, and there is a charge placed at a distance a by 2, and that this distance is perpendicular to the surface, this square surface. Okay, so let us write this point. Okay, this is a charge q is placed at this particular position. This is a by 2. Okay, so what will be the flux through this square surface? What will be the flux through this surface? So as you know, this is very simple question. You have to consider a cube. Okay, consider a cube here. Okay, I'm not very good in drawing a cube, but anyway, so you have to consider a cube. Okay, let me just make like this. Yes, this will go like this, this will go like this, and this will come here, this will come here. So let us connect with this like this. Okay, so you have to consider this as a sphere. Actually we have like this. If you draw, then it will come as sphere, cube. Okay, so this is a cube now. Okay, so you can see we have to consider that this particular square surface which is given is a part of a cube of side A. So the charge which was placed at a by 2 perpendicular distance from surface, given surface, square surface, is now enclosed by the whole cube. So you know, the total flux will be due to this total flux linked with all the surfaces will be Q by epsilon naught, but flux will be equally distributed. Okay, equally, like see, if I just draw this field lines will be actually going equally through all the surface. So that's why the total flux Q by epsilon naught will be equally shared by all the surfaces. So the flux through each surface will be 1/6 of the total flux. Okay, so this is the flux. So option 4 will be the correct answer for this question. This is very simple question, but you have to understand and apply the concept. So with this, I'll stop it here. We'll take up next topic, like next subtopic later. There are electric field. See, field we have already discussed, electric potential, then dipole, etc. Okay. So all right. So thank you for your patience. Bye for today.